Hi everyone, here we go again. So after learning about 9.1 on redox reaction, we learn about how to balance redox reaction under acidic and basic conditions. We learn about redox titration. We learned about the Winkler method. Now for 9.2, what we're really doing is putting what we learned in 9.1 into practical use. Like, what's the point of this electrochemistry? Now, obviously has something to do with electricity, right? So let's take a look at topic 9.2, electrochemical cell. Now, there's two types of electrochemical cell. There's this one, Voltaic cell, and there's another called electrolytic cell. Now, a voltaic cell, sometimes you may notice that some people might call it galvanic cell. It's really the same thing. I'm not sure why they have two words for the same thing, but that's what it is. Now, a voltaic cell is a cell where chemical energy is converted into electrical energy. So let me tell you it again. Energy in chemicals are converted to energy in electricity. Obviously, with electric energy, you can use it to do work, which is very important nowadays. Imagine, if you have no electricity at home, it's going to be a long day. Now, the reaction inside a voltaic cell are spontaneous reaction. What that means is that the reaction happens spontaneously. It happens on its own without any input of outside energy. It just happened. Okay, that's what we call spontaneous. A lot of reactions are quite spontaneous, where no extra energy is needed for a reaction to occur. Now, the reaction also has to be exothermic, which we already know what that is. Now, in a voltaic cell, there are two electrodes. There is the negative electrode and the positive electrode. The negative electrode is where you'll see oxidation occur. Now, oxidation in this case means losing electrons. The positive electrode is where reduction occurs, and we call this electrode the cathode. The oxidation electrode is called anode. Now, it's pretty easy to mix it up, in the beginning, especially what I'm going to tell you next. But I'm going to have to try very hard to memorize that. So, anode is the negative electrode, and this is where oxidation occurs. Cathode is the positive electrode, and this is where reduction will occur. All right? Here's another cell called electrolytic cell. This one is the opposite. This is when we use electrical energy to do something to the chemical. Okay, so we're kind of converting electrical energy into chemical energy. So we're using electricity to do chemical work. Whereas for this one, we're using chemical energy and turn it into electrical energy. Here, using electrical energy to do chemical work. This type of reaction are non-spontaneous, meaning that it doesn't just happen. Okay? The reaction has to have some sort of outside energy to be inputted in order for this reaction to occur. Hence, electrical energy has to be inputted. So what that means is that when we look into an electrolytic cell tomorrow, you'll see a battery in place. Whereas today, we're going to look at a voltaic cell, you'll actually see no battery in place because the reaction itself is the battery. Now, this is the confusing part. The electrode that does the oxidation, which is the anode, is positive, which means the negative electrode is the one that does the reduction. Now, this is actually the opposite from a voltaic cell, because if we look back to the voltaic cell, Negative electrode does oxidation. Positive electrode does reduction. Here, positive electrode does oxidation. Negative electrode does reduction. Try and memorize that, I guess. Try not to get confused. It's pretty easy to get confused here. All right, let's have our concentration fully on voltaic cell today. So, I'm going to show you how to build a voltaic cell. Okay? Normally, we're supposed to build this together. I give you some metal strips, I give you some solutions, and we're going to put this together and we're going to test that. Ooh, it does generate electricity. But, well, we know our situation. I'm so sorry for the fact that we can't do this, but I guess we can do it on paper. I know, it's not the same. So, to build a voltaic cell, you need 2 metal strips, and they have to be different metal. Okay? One metal does the oxidation, and the other metal does the reduction. These metal are dipped into a solution. Now, let me tell you what the solution is in a sec. And connecting the 2 solutions together is this thing called the salt bridge. All right. Let's put one of these things together. Let me just use various color. So I have 2 beakers. Okay. Obviously the 2 beaker houses 2 different solutions. Okay. Now, in each beaker, I have some sort of metal strip. This cell that I'm specifically doing is called Daniell cell. Okay, discovered by obviously a scientist named Daniell. So I have this zinc strip in one solution, and on the other solution, I have a copper strip. All right? They are linked together by an electrical wire. This can be any wire, most likely copper wire. Okay, the one that you used back in grade 9 with the alligator clip. Wasn't that fun? So, now, what are these solutions? What's in here? Now, it's very specific in terms of what you have to put in here. Since this is a zinc strip, this solution right here has to involve zinc. Now, what I'm choosing here is zinc sulfate. Okay? It has to be a solution. Now, what about this? Well, if the solution here has to involve zinc, the loose solution here has to involve copper. Well, I'm going to choose copper sulfate. Okay? Now, since these are solutions, they are not going to exist as copper sulfate. We know they will dissociate to be copper 2 plus and sulfate. For the other electrode, zinc 2 plus and sulfate. That's what's going to happen, okay, in real life. Now, because of this, zinc will start to notice. Zinc will notice that, hey, look at these SO4. I want to bond with this SO4 because this SO4 is free-flowing in this solution. I want to bond with it. So what is zinc going to do? This is what zinc is going to do. Zinc is going to leach. Okay? Zinc is going to do this. I'm going to leach out and become zinc 2 plus. However, you'll notice that zinc becoming zinc 2 plus lost 2 electrons. Remember how to balance that the other day? Where did the electron go? Well, let me just tell you this right now. That the electron, 2 of them, actually will go through this wire. Okay? So the zinc metal here leached out to become zinc 2 plus, and the 2 electron will go through this wire. So let me write this half reaction at the bottom. Okay, this half reaction states that Zn as a solid decompose to become Zn2 plus and 2 electron. The electron will go through the wire. The zinc ion will leach into the solution. So if you think about it, as this proceed, this zinc strip will get smaller and smaller and smaller, because as it continues to leach, it continues to lose the zinc metallic property. Now, the reason why zinc is here is because it's C sulfate. So they obviously want to get together, but you know they're not going to get together for a long time because because it's a solution. They are soluble in water. So they're going to be in this beaker. You'll see a lot of these zinc 2 plus, and you'll see some of these SO4 2 minus. All right. Are you guys still with me? If not, you can always rewind, right? So let's go and look at the electron. Electron. The 2 electron will continue to travel through this wire. Continue and continue and continue. Well, guess what? Where is he going? Well, it looks like he's going to go to the electrode containing copper. Why do you think he wants to go there? Well, let's take a look at copper 2 plus. Copper sulfate dissociate to become copper 2 plus and sulfate anion. Copper 2 plus, note the fact that, hey, there's 2 electrons coming down. I want to be part of this. I want to come in here and hook up with those 2 electrons. I want to come here and capture those 2 electrons and become Cu solid, right? Cu2 plus, adding 2 electrons will give you Cu. Let's write this down here. So Cu2 plus 2 electron will give you Cu in solid form. That's what Cu2 plus is going to do. Seeing that the 2 electrons are coming down through this wire, I'm going to come over here and get together with these 2 electrons to turn myself into an atomic copper. So, in reality here is this: as this reaction proceeds, this copper strip will get bigger and bigger and bigger, while this zinc strip will get smaller and smaller and smaller. Hope that makes sense. Now, as you can see, these copper are going to come in here to bond with those 2 electrons, or not bond, but then to capture these 2 electrons to become copper metal. That leaves a lot of sulfate in this solution. Here, we see a lot of zinc and sulfate in this solution. Are they just going to stay there like that? Well, it's pretty unstable for them to stay here like this, if you think about it. So, this is where the last piece of this build will come in. What I have here is called a salt bridge. All right, it's called a salt bridge. What's in this salt bridge is certain type of salt. Now, it can't be very specific in terms of what type, but some people use KCl. Okay, I use a lot of KCl. Some people use sodium sulfate. Okay, sodium sulfate. It really doesn't matter. It really doesn't matter because this is not that important. So let's say I use KCl. I put KCl solution here. Okay. Like all solution, KCl is not going to stay KCl. They are going to dissociate. Now the question is, when they dissociate, where would K go? Where would Cl go? Well, funny enough, Cl wants to come over here. K want to come over here. Okay? Why? Because K sees the situation and see, hey, lots of SO4. Cu went on to become Cu solid. These SO4 are here and with nobody to play with. So as a cation, I want to bond with this anion. So as a result, K comes in and sort of got together with sulfate to form K2SO4. Alright? Now, it's not going to stay together very long, I can tell you that right now, but it is actually a way to stabilize the negative nature of the solution. Now, looking to the other side, Cl. What will Cl do? Well, do you notice that there's a lot of Zn and not as much SO4? So there's actually double the amount of positive ion than negative ion. This is not a healthy thing, because as this continues to circulate, you're going to make more and more and more of these, because more and more of these will dissociate to become more and more of these. So to stabilize what's going on, these zinc will be captured actually by the Cl to make zinc chloride. But again, zinc chloride is soluble. They're not going to last forever, but at least it's there to stabilize what is going on in here. Maybe I shouldn't have done that. Okay. You get it? Okay. Let's go back and just kind of summarize what's going on here. Okay. So we started with zinc metal. Zinc metal leaches out to become zinc 2 plus, and the 2 electron that you get from it will go through the wire. Okay. By going through the wire, it goes into the electrode that has the copper. When copper sulfate dissociate, copper 2 plus will go into the metal strip and hook up with the 2 electron to become copper metal. Alright? So you can see the direction of electron is overall this way. Okay? Overall this way. Overall this way. Now, the sulfate here will, I guess, bond with the potassium from the salt bridge made it of potassium chloride, and the chloride here will bond with the zinc that is being leached out by zinc metal, So hopefully looking at this build, maybe watching it a few times, you will understand exactly how a voltaic cell works. Now, let's go over the terminology. Your favorite part. Okay, look at this reaction right here. Zinc becoming zinc 2 plus with 2 electrons. I'm pretty sure you guys know that this is an oxidation process. Okay, losing electron, that's oxidation. If you look at here, copper 2 plus combined with 2 electrons to give you copper metal. I'm sure you guys know that this is a reduction process. Together, this is a redox process, and we know everything about redox process, right? So as an oxidation electrode, this electrode is obviously the anode. Okay? And anode in a voltaic cell is the negative electrode. Now, since this electrode is the reduction electrode, that means this is the cathode. Being a cathode in a voltaic cell, this is the positive end of the cell. I hope you guys understood that. Okay, if not, as I said again, you can go back and rewind and see if you guys get it. But I do have notes in the next few pages. Okay? Hopefully that will help. But that's how you would build a voltaic cell. This is something that we would have built together. Get you guys to pair up in 2s or 3s, give you some solutions, give you some metal strips, and you guys built one. And you test for various things. Now, what are you testing? What can you test? How do I know if my voltaic cell is working or not? Well, remember, a voltaic cell uses chemical energy and turn it into electrical energy. So what that means, as electron moves through and moves through and moves through, you're generating electricity. If you remember back in grade 9, how do you test the fact that you do have a difference in potential? Potential difference, right? Hey, you can insert one of these guys. Remember voltmeter? If you insert a voltmeter right there, you're actually measuring the amount of potential difference in the wire, right? How much power or how much voltage electron is carrying over here versus leaving the voltmeter. So you should get a number in volts. What that means is this: you're actually generating electricity. You're generating a whole lot of electricity using chemical energy. Wow, electricity. Thank you, Pikachu. I needed that. Wow, so that's the voltaic cell. Now, let's take a look at some of these description about the voltaic cell. I'm sure you guys can read this part on your own. It talks about, the pathway of electron transfer, the Daniell cell that I was trying to draw out here, and I guess whatever you don't understand with my illustration, you can always read this, read Cognity, and see if you can understand exactly what's going on, how chemical energy can be converted into electrical energy. Okay. Now, this part is not really in your curriculum. It's more for, the regular grade 12. Can we calculate the amount of energy? Can we calculate what the voltmeter is going to give me? Of course, the answer is yes. Okay. All you have to do is know what is what we call E naught for every half reaction, and we sum it up. Okay. For an oxidation reaction of zinc, you can look at table 24 in your data booklet, and you'll find that this reaction is worth 0.76 volts. For the copper reduction reaction, okay, this is worth 0.34 volts. Now, you'll notice that in table 24, all the reaction is actually given as, it's actually shown as an oxidation reaction. And in it, you'll just take the difference of these two numbers, and that will be your overall net redox energy value. But in this case, I took the liberty to kind of turn them around, okay, have them both as positive value, and all you have to do, of course, is to sum these two numbers up to get what we call the net redox reaction voltage. So what you'll find in your voltmeter is 1.1 volts. So this Daniell cell is worth 1.1 volts. Now, is it always 1.1 volts? That's not that much. Well, the number here is dependent on your electrodes. Okay? The metal that you're going to use. The solution that you're going to use. They all play a huge role in terms of what number this is going to be. So if you're going to use the zinc and copper combo, well, you're going to get 1.1 volts. Okay. Is that a lot? Well, I guess it'll power your little electrical toy. Don't expect that to give you a car battery-like type of power. Electricity, you're not going to get that. All right, so here it is, showing you exactly what the anode is doing. Okay, seeing the fact that oxidation occurs here, and the electron is going to go through the wires. That's the whole point of the anode. And the other side, which is the cathode, okay, taking in the electron, which is a reduction reaction, showing you exactly how this whole thing is put together. Oh, one more thing. We mentioned about the zinc getting smaller and smaller. We also mentioned about the copper getting bigger and bigger. What about copper sulfate solution? Now, copper sulfate solution is naturally green in color. And we know some of the copper went on to become copper metal. Some of the sulfate, I guess, bonded with the potassium in this illustration. So, are there any more copper sulfate if you think about it? The answer is no. So, as this reaction proceed, you'll notice one more thing other than this is getting smaller and this is getting bigger, is that the green is getting paler. Less and less green. Okay? Then you'll know that, oh, you know what? My voltaic cell is actually working. I built a good voltaic cell. At least the one that works. All right. Salt bridge. All right. Our illustration was on KCl. Of course, you can always use sodium sulfate, potassium nitrate. They're all very good salt bridges. All right. Cell diagrams. So how do we illustrate these things on paper? Well, on paper, you write your anode on the left side and cathode on the right side, separated by two vertical lines. All right. So if your voltaic cell design is based on the Daniell model, you'll have zinc metal with zinc ion on, of course, the anode side, and on the cathode side, you'll have copper ion and copper metal. Okay, showing the oxidation, showing the reduction. That's how you would illustrate cell diagram on paper. All right, hey, I have 2 questions for you to do. Okay, the first question, I want you to do exactly the same thing I did. I want you to draw a voltaic cell. Obviously, you're going to be using different things. You'll be using cadmium and cadmium nitrate as an electrolyte. And on the other side, you'll use nickel and nickel 2 sulfate as an electrolyte. Now, you may be asking right now, which one oxidizes and which one reduces? You told me zinc oxidizes and copper reduces, but you told me that. How do I know here which one is the oxidizing part? Well, this is based on electrostatic series, if you remember what that was. The last time we used electrostatic series, I think we were doing single displacement. Okay, this time we're going to use it again. And I tell you right now that if you were to look at the electrostatic series, zinc is higher up than copper. Okay, so since that is the case, zinc is the one that oxidizes, copper is the one that will reduce. So in Google Classroom, I will provide you with another copy of the activity series, and you check to see where cadmium is being placed. Okay, cadmium is being placed and where nickel is being placed. So whoever's higher in the activity series is the oxidizing part. All right, make sure you do these questions. And of course, I have another one for you. Do exactly the same thing, but this time, silver versus nickel. The electrolyte here for silver is silver nitrate. The electrolyte for nickel is nickel nitrate. I think I made a mistake here. It should be NiNO2. Okay. Hopefully you can fix that and show me exactly how this is going to work. Okay. Anyway, that's it for Voltaic Cell. So the next day we're going to look at Electrolytic Cell and see how that is different. We know the difference already, but let's see how it works. If we were to build one, which we should have, how do we build one of those? It's a lot easier to build one of those than the Voltaic Cell. This is actually a lot more work. Anyway, have a good day. I'll see you tomorrow.